Welcome to this lecture series in real analysis. In this lecture, we'll be looking at the abstractification of what we have so far seen in the context of rationals. So let's recall what we have seen. We defined what are rational numbers, and then we defined an addition and a multiplication on them. And we observed that the following properties are satisfied. So this was called associativity, this is commutativity, this is additive identity and multiplicative identity, and this was additive inverse. So for each for each rational number A, there is another rational such that if you add the two, you get the additive identity. Similarly, for multiplicative inverse, you can take multiplicative inverses of any non-zero element. This was distributivity. All right, so these were already familiar from high school. And then these are some properties which pertain to the ordering on the rationals that we define. So it says that if we have any two rationals with one less than the other, then you can add any other rational to both of them and again preserve that same inequality. Something like that also happens in the, in multiplication. So if you have A less than B, then you can multiply with any positive rational and retain the inequality. So this is all positive rationals. Q plus means those rationals which are positive. All right. So today we will be abstracting this out to what is called a field, and the point of all this is to at least define an object first which does not have the defect that we saw that rationals have. What was the defect that we observed? The defect was that an upper bounded set, or rather I should say, suppose you have a subset of rationals which has an upper bound in rationals, this may not have a least upper bound, and that is not very nice. Okay. So first we need to define what is a field. This will capture the left half of the previous slide. So let me just get started directly. So a field is a triple where this is a set. This is something that we will talk about, these two things. So this is just a set, a non-empty set, but let me just say a set. So field is a triple where f is a set. This guy is a function from a f cross f to f, and this guy is a function from f cross f to f. So this is called the addition function, and this is the multiplication. So this is merely mimicking what we observed in rationals. You can add any two rationals, and you can think of it as a function which consumes two rationals and outputs a rational. So that's the addition. Similarly for multiplication, but we are abstracting it out. So we do not have a definition for it. It's not like there is some definition to addition. It's just that it is a function. Multiplication is another function which satisfies the same properties that we expect addition and multiplication to satisfy, or which we have already seen addition and multiplication satisfying in the context of rationals. Okay, so before we proceed, this of course sends alpha comma beta to tautologically to this thing, but instead of writing this, we will write it like that. It's just better. So this is just a change of notation. This function of course takes this pair to that. No question about it. It's a notational thing. But instead of writing it this way, we will write it that way because that is much more readable. We will commit the same crime with multiplication. So it takes alpha comma beta to this thing, which we will write as that. Or an even more heinous crime would be to just write like this. And this is what we will do. We will even suppress the dot. Okay, so we insist several properties be satisfied. The first is associativity. So it says that alpha plus beta plus gamma equals that. So this says that Whether you add the last two first and then add the result to the first, or you add the first two first and add the result to the last, it's the same thing. And same for multiplication. Right? And this is, of course, for all alpha, beta, gamma in the field, in the set F. Okay. So this is associativity property. We already saw this property true being true in the rationals. Okay, commutativity. It says, so yeah, before we continue, let me just say what this looks like in the more formal notation. It looks like, where do I write that? Let me write the expression for the one on the right, this one. So in the more formal notation, this would look like that. So this thing is actually that thing, but of course this is far more readable than that. All right. So commutativity says that alpha plus beta equals beta plus alpha, and alpha beta, I'm suppressing the dot, is beta alpha for all alpha and beta. Okay. Additive and multiplicative identity. So additive identity axiom demands that there exists some symbol which we denote by 0. So this 0 does not have any bearing on anything that we have seen so far. It is just a symbol. There is a reason why we have chosen this symbol. So there exists some element in F which we denote by 0 such that alpha plus 0 is alpha for all alpha. And this is called an additive identity. And similarly, there exists a symbol 1 in F such that 1 times alpha is alpha for all alpha. Okay? So this is, we insist that there is such an element in F with this property. We denote it by this symbol for good reason. And before we continue, let me argue that these are unique. So the axiom only insists on the existence of such a thing, but it automatically follows that these are unique. So let me argue the uniqueness of the additive identity. This guy is additive identity, this guy is multiplicative identity. So let me argue why additive identity is unique. So if 0 and 0 prime are additive identities, then what is 0 plus 0 prime? So in this equation, think of this as the additive identity and this as just some element of the field. Then this better be 0. But by commutativity, the left side is 0 prime plus 0. And this time think of this guy as an additive identity and this as just some element of the field. So we get this is equal to 0 prime. And hence 0 must be equal to 0 prime. That's it. Similarly, you can argue the uniqueness of the multiplicative identity. All right. So now I think, additive and multiplicative inverse. So we insist that for all elements in the set F, there exists some alpha prime such that if you add the two, you get 0, meaning the additive identity. All right. And similarly, we have an axiom for the multiplicative identity. For all alpha in this thing, so everything except the additive identity, there exists some alpha prime. Let me not say alpha prime, let me say beta in F such that if you multiply the two, you get the multiplicative identity. Okay. So just like in rationals, there is only one such alpha prime. Alpha plus alpha prime is equal to 0 already means that there is only one such alpha prime. Even though we only insist on the existence of alpha prime, it automatically follows that there is only one, and I leave that as an exercise. This alpha prime is called the additive inverse of alpha, and the notation for it is minus alpha. So this is what we use to denote the additive identity. Sorry, this is what we use to denote the additive inverse of a given element. Okay, and to denote the multiplicative inverse, we either use that symbol or use this symbol. Anyone is fine. Okay, so these two are unique. The additive inverse and the multiplicative inverse, if they don't only exist, they are actually unique, and I would like you to show that on your own. Okay, the last axiom is distributivity. So it says that alpha times beta plus gamma is alpha beta plus alpha gamma. This is true for all alpha, beta, and gamma. Okay. So all of this may look very complicated, but all we are doing is we are abstracting out what we have already seen to be true in rationals. We are saying just consider some abstract object which satisfies those properties. Now, there could be multiple such objects. One such object is, of course, the rational numbers with the usual addition and the usual multiplication that we saw. Who knows, maybe there are other such objects. As of now, it's unclear if there are other such objects. Okay. And now, before we continue, here are two properties that we should observe, two or maybe three properties. So for any field, pick two elements alpha and beta. And the first says that if you multiply alpha with 0, you get 0. So this is again the same thing that happens in rationals. The other one is if you multiply by the additive inverse of 1, if you multiply alpha with the additive inverse of 1, you get the additive inverse of alpha. And the last one says that multiply the additive inverses of alpha and beta, you get same as multiplying alpha and beta. Okay, so let's prove them quickly. So proof of 1. 1 is proven by observing that this is equal to that, right? Because 0 plus 0 is 0. 0 is the additive identity after all. So this is the case. And therefore, by distributivity, or maybe let me use commutativity once so that there is no confusion. So we used commutativity on the left side. So we have that. Now use distributivity. And on the right side also use commutativity because it's just more convenient. So what we see is that this, whatever the symbol is, let's call this beta. So beta plus beta is beta. Okay, so you add the additive inverse of beta on both sides. And what you will get is, so let's call that beta. So we have beta plus beta is equal to beta. Now we add the additive inverse of beta on both sides. So we get beta plus 0 because this much is 0 and same as that. But beta plus 0 is beta. 0 is the additive identity. So beta is 0. And beta is nothing but alpha dot 0 or 0 dot alpha. It's the same thing by commutativity. So we have this. So this proves 1. Okay. So to prove 2, we have 1 plus minus 1 times alpha is same as 0 times alpha, which we have already seen to be equal to 0. So this implies by distributivity 1 times alpha plus minus 1 times alpha equals 0. But 1 times alpha is alpha. So alpha plus that thing is 0. And therefore, since additive inverses are unique, this guy has to be the additive inverse of alpha. And hence this is minus alpha, because minus alpha is the notation for the additive inverse. So that proves 2. And to prove 3, so to prove 3, we have minus alpha is, as we just saw, equal to this, and minus beta equal to that, and hence minus alpha times minus beta is equal to minus 1 dot alpha minus 1 beta. Using commutativity, we can write it as this. And now just focus on the first two. All right, so we are multiplying minus 1, or the additive inverse of 1, with something, and hence the answer is the additive inverse of this guy. So this is minus minus 1. Right, we are using 2 here. But what is the additive inverse of the additive inverse of 1? It is equal to 1, which is equal to alpha times beta. So maybe here is one more property that I could have mentioned. Let me call it maybe 1 prime. So its additive inverse of alpha is alpha. And the reason is very, very simple. The reason is alpha plus this is 0. So what is the additive inverse of this guy? Additive inverse of this guy is that. And therefore the additive inverse of alpha is alpha. Trivial. Okay, so these are some few properties that hold in any abstract field. Of course, they also hold for rational numbers. Okay. Now for the more interesting bit, or yeah, before that, let us see an example of something that is not a field. So consider the set of all integers. This is the thing. Equip this with the usual addition and the usual multiplication of integers. And this is not a field. And there are multiple ways to see this, but one axiom that is not satisfied here is the following. 2, the integer 2 does not have a multiplicative inverse in this set. So that shows that this is not a field. Okay. Now we come to what are called ordered fields. So yeah, before we proceed, maybe I should mention one thing. So even though we defined a field as a triple, you may see phrases like let F be a field. So this is an abuse of terminology or abuse of notation, and it's a good abuse. So instead of writing let this be a field. So basically we suppress these two symbols, because every time writing them makes things cumbersome. Unless one is trying to really discern between, suppose we are working with two different fields and their addition and multiplication are they behave very differently or something. Or maybe you have two different kinds of addition and multiplication on the same set, so that now it is important to distinguish between them. Only then you would explicitly mention the symbol for addition and the symbol for multiplication. But 99.9% of the time you don't need to. There is no confusion caused if you write something like this. So with that remark, we want to define what is an ordered field. So an ordered field is a pair where this itself is a field, where F is a field. So again, when we say that, where F is a field, we are suppressing the data of addition and multiplication that is implicitly present in this statement. Very, very rigorously, what we should say is that an ordered field is a quadruple where this thing is a field and so on. But again, doing things this way is suitable for computers, not humans. Okay, so an ordered field is a pair where the first thing itself is a field and the second thing is a total order. Field and this is a total order. total order on F such that some two properties are satisfied. But before we write down those two properties, let us recall what is a total order. So a total order is a partial order where any two elements are comparable. So in other words, for all alpha and beta in F, either this will happen or that will happen. That's what it means to have a total order. Just like the ordering on rationals we saw is a total order, the ordering on integers is a total order. We are insisting, we are abstracting things out. So we are saying an ordered field is a pair where the first thing is a field and this thing is a total order on the set F such that something happens. So yeah, so the point is the field axioms that we just saw, the axioms that we saw here, they are abstracting out the algebra or the arithmetic of rationals, right? Addition and multiplication. While this will be abstracting out the ordering on rationals. Okay? So an ordered field is a pair where this is a field, this is a total order on F, such that the arithmetic and the ordering, they interact well. So the first property is if alpha and beta are in F with alpha less than beta, then and again, what is this symbol? This is a little different from that, right? So this symbol means alpha is less than equal to beta, but alpha not equal to beta. So that's what that means, and we have mentioned this earlier in earlier lectures. Okay, so if we have two elements in the field with this comparability, then that is preserved if you add any element of the field. So it behaves well with addition. This ordering that we have behaves well with addition. And the second one is that if alpha and beta are in F with the same thing, then alpha gamma less than beta gamma for all gamma in F satisfying this thing. Okay, so you can say that, I mean, this is just one way of saying it. The formal statement is here, but you can say that if alpha less than beta, then alpha gamma less than beta gamma for all positive gamma. Okay. So this is called an ordered field. So yeah, maybe you can formally define. So the set this is called the set of positive elements of F. Right, and let us give this a name. This is denoted by F plus. That's a notation, and this thing will be denoted is the set of all the non-negative elements of the field. And surely you can define for yourself what is the set of all the negative elements. Okay, so we have defined what is an ordered field, but let us look at some properties. Fine. So another abuse, we say let F be an ordered field. We are not saying this be an ordered field. So again, this symbol is suppressed. So we are suppressing the addition symbol, the multiplication symbol, and also this symbol. This is another abuse, but it's a good one. Okay, so fix an ordered field, and suppose we have two elements alpha and beta. Then first property says that if alpha is positive, so yeah, so this is just another way of writing 0 less than alpha, right? So if alpha is positive, then minus alpha is negative, meaning it is less than 0. So this is the additive inverse of alpha. Why is that? The reason is we are already given that 0 is less than alpha. That's what that is. So we add on both sides the additive inverse of alpha. So we are using property 1 here. Just think of this as gamma and use property 1 or the axiom 1 of an ordered field. So we have an inequality, we are adding the same thing on both sides, so inequality will be preserved, and that's what gives us the left side is minus alpha, the right side is 0. This is minus alpha because this is the additive identity. You add the additive identity to anything, you get that same thing, and alpha plus the additive inverse of alpha is 0, so we get that. So this is true. Second one, if we have two positive things, then their sum is also positive. So the reason is, or one way to argue is the following: we are given this, that alpha is positive. Let us add beta to both sides. So if you add beta to both sides, inequality will be preserved and you will get this. And we already have that beta is positive, and now by transitivity we get that, right? So I mean, this thing was a partial order, so transitivity holds, and therefore we have that. Okay, same for the product thing. So if alpha and beta are positive, then their product is also positive. So it's the same proof as the previous one, except in the previous one, here we were using property 1. Here we will use, or rather axiom 1, here we will be using axiom 2. So we have this to be given, multiplying beta, which is positive on both sides. So we can do that without disturbing the inequality. We have that. Just multiply beta on both sides, and immediately we get what we wanted by using axiom 2. Okay. So this says that if you take additive inverses on both sides, the inequality is flipped. Why is that? So what we have is alpha less than beta. This implies adding additive inverse of beta on both sides. We get, using axiom 1, we have that, and now add additive inverse of alpha on both sides, which gives us the correct thing, because this is 0 and 0 just adds with this to get that. So we have that, and this is what is written here. Okay, lastly, if we have two negative things, then their product is positive. And the reason is very simple. Alpha is negative implies this is positive, right? That is the previous one. Just use the previous one, we get that. And similarly, we are given this is the case, and hence that is positive. We have shown that product of two positive things is positive. But we also observed previously that the left side is nothing but alpha beta. So that proves this guy. Okay. So now we have one negative, one positive. The product is, we are claiming negative. So the reason is we have alpha less than 0, which implies minus alpha greater than 0. And since beta is given to be greater than 0, we get this is greater than 0 because the product of two positive things is positive. But this is equal to, or this implies that minus 1 dot alpha dot beta is positive. Multiply both sides by minus 1. Or, yeah, multiply both sides by minus 1 is as good as taking additive inverses of both sides. So the inequality is flipped as we proved. But the left side is nothing but alpha beta. So think about it if it isn't clear immediately. Okay. So if alpha is non-zero, then alpha square is positive. So there are two cases. If alpha is positive, then of course alpha times alpha is positive because product of two positives is positives. So we get alpha square is greater than 0. If alpha is negative, then minus alpha is positive, and then minus alpha times minus alpha is positive because product of two positives is positive. And minus alpha times minus alpha is same as alpha square. So this I'm not writing. Okay. 1 is greater than 0. So the reason is 1 square, 1 times 1 is equal to 1. And yeah, so one thing perhaps we should have mentioned, that in the field axioms, I think we need to assume that the multiplicative identity is different from the additive identity. So this should be, I think, one of the axioms. I'm not too sure, but let's assume that. I mean, just put it there, even if you can somehow derive it with what you have said, doesn't matter. We are assuming that 1 is different from 0. So now basically using this we get that 1 is greater than 0, because just think of 1 as alpha. Since 1 is different from 0, alpha is non-zero, and therefore alpha square is positive, but alpha square is nothing but 1 because 1 square is 1. So this follows from the previous one. Okay. And then we have, if you have a positive thing, then its multiplicative inverse is also positive. So why is that? If the multiplicative inverse were negative, so let's say if this is negative, then since alpha is positive, the product of a positive and a negative is negative. We would have gotten that 1 is negative, but that contradicts the previous inference. So that's a contradiction. So therefore, we must have that 1 by alpha is positive. And lastly, this is an exercise. Exercise because I'm tired. So it's the commonsensical thing. Alpha less than beta and gamma less than delta means alpha plus gamma is less than beta plus delta. The commonsensical thing and very easy to prove. Okay, so these are some properties that we already know to be true in rational numbers, but they follow from axiomatic treatment themselves. Okay. So here are some more exercises. Fix an ordered field. Suppose we have two elements, both of which are non-negative. Then for any natural number n, these three things I want you to show. Okay, where this notation a to the n just means what you think it means, the natural definition. And yeah, so this abstracts out all the properties of the rationals that we have seen so far, the order properties and the algebra properties. And this is what we will use to define the real numbers. Basically, the defect in rationals was that not every set that was bounded above has a least upper bound. We will define reals by insisting that you have such an object, an ordered field, which does not have this defect. So that will be the definition of real numbers. Then the headache would be to show that actually such a thing exists. Just because one can define something doesn't mean it exists. So the headache from there would be to actually construct real numbers. And another headache would be the uniqueness. So we will talk about all of that. With that, I want to end this lecture. As usual, like, comment, share, subscribe. And I will see you next time.